Good day, everybody. A very warm welcome to all of you. It is 4 o'clock sharp. We will probably offer a minute for those who are just getting settled extra before we kick off. But this session will be recorded, so anyone who misses anything will get whatever they need. So we're not going to be hanging around for too long, but just a little bit of let's say courtesy time for those who intended to catch the beginning. I know all our time is valuable, so yeah, I said a minute, so I think let's get cracking. As I said, warm welcome, and what a privilege it is these days to be able to be with you all from no matter where you may be. We're excited to share the best thinking and strategies we have on the topic of analytical geometry today. But thank you to you, and well done for being here. And by doing this, you're an example to all teachers out there. You're prioritizing your professional development. The Answer series is South Africa's best-selling provider of grade 8 to 12 study guides across 16 subjects, for those of you who are not aware. Now, we're complementing our study guides with teacher development. And as we all know, mathematics performance in South Africa is sort of against the ropes, and we strongly believe it needn't be that way. And we're on a quest to provide the best form of teacher professional development in South Africa for FET mathematics, timed with the amended teaching plan and delivered to you through the convenience of your mobile device or laptop, wherever you're consuming this webinar or the support material we'll offer you in your home, or perhaps at a coffee shop or a friend's house, or even at school. We'll be offering this teacher support material and on a topic basis, and the formula that we think achieves this this best form of teacher development has 3 ingredients. And bear in mind, this is the first version. It's 2021. We're going to be doing improved versions in the future, but we think the best opening formula is a 3-part thing, which is this opening webinar, which you're attending right now. Well done. The second part is an online course in which there are both videos and quizzes. And the third part is in-class materials that you can download and share with your learners. The purpose of the opening webinar is to set the scene for the topic, to outline some strategies, and to have you be as best orientated about this particular topic and how it's featured in recent examinations, how learners have coped with the different questions, etc., etc. The second part, which is the online course, we call it a micro course, is the next step. It's 3 hours. You will receive the link at the end of this webinar, and at a location and time that suits you best, go through the expertly compiled videos as well as the quizzes that follow them. Don't worry, the videos are compressed to 1/10 of their normal size because we've had the technology to compress the videos, so it's very data efficient. The quizzes are important because the requirement for application is as relevant for us as adults as it is for our learners. And then the last ingredient, as I mentioned, is that you will receive materials that you may share with your learners. The materials are available via PDF and can be accessed via download from within the micro course. If that was all a mouthful, just monitor your email and follow the links from there. Now, some of you might be thinking you only signed up for a webinar. However, by signing up, you've qualified yourself for both the online micro course as well as the in-class materials that follow this webinar. This teacher support program is so new that the SACE accreditation is being finalized, but we have been informed that SACE points will be retrospectively given to teachers that fully complete the course. So stick with it. Lastly, we can't provide South Africa's best teacher professional development without your help. There will be 2 opportunities to provide your feedback. Firstly, during this webinar, we will give you a link in the Q&A towards the end to just get a few of your thoughts about how it went and what you liked and what you didn't like. Lastly, at the end of the micro course, as a requirement to achieve its completion, we would love your considered input into what could improve things and how things could be better. Remember, we want to create South Africa's best version of and most modern form of professional teacher development, and we'd love your help with that. With all of that taken care of, I now hand over to the author of our FET Maths study guides and founder of the answer series, Anne Eadie, who will present today's webinar on analytical geometry. One more thing, please make use of the Q&A section in this webinar. If your question is not maths related, we will respond immediately or as soon as possible. If your question is maths related, we'll respond at the end of the presentation. My encouragement to you is to write your questions when it occurs to you rather than waiting until the end and then you've forgotten your question. So just carry on popping them in there and we'll make sure to address them in the Q&A session after the presentation. So that's enough of me and from me. I didn't introduce myself. I'm George Eadie. I'm the CEO of the Answer Series. I'm proud to be presenting my team and actually my mother, Anne, who will take you away into the land of analytical geometry. Enjoy.
Thank you, George. And once again, a really warm welcome to everybody. Here you are on day 1 of term 2. I'm sure exhausted after your first day back, and really appreciate that you are here to join us in the improvement of the state of mathematics performance in this country. We would like it to be above 35%, an average performance for those getting higher than 40% for mathematics. We really do need to end or to aim at the top end of the scale, rather than have such huge numbers performing so poorly. Analytical geometry, I really look forward to sharing this with you today. For me, it is one of the most valuable modules in geometry for all it has to offer. It is an ideal vehicle for promoting problem-solving skills. And over time, it has also been called coordinate geometry, and it certainly is all about coordinate points. But I like it to be known as analytical geometry because then we know it is about analyzing the sketch, the information, analyzing what you need when answering questions, making deductions. And in any topic that we deal with, there is content that is absolutely vital. Content is key. And we will be sharing with you what we at the Answer Series refer to as the Analytical Geometry Toolkit, which is quite fun and makes it such an achievable topic for learners to excel in. But apart from the content, it is the reasoning that is crucial. Blind procedural responses and blind use of formulae and standard forms miss the point and result in poor performance. The analytical thinking skills that learners can acquire in analytical geometry draw from several areas of maths: algebra, Euclidean geometry, trigonometry, and graphs, and in return impact the mathematical thinking required generally in mathematics. Analytical geometry is almost always problem solving, just in that the drawings will always be ones that you've never seen before. The questions can, of course, be on all cognitive levels of thinking, sometimes including ones at which you could just chuck a formula and probably get your marks with absolutely no understanding. If you've read the formula off the formula sheet correctly, as is so often the case, of it not being in fact the case. I just want to remind you that the materials that I will be discussing with you today, first of all, there is a lot of detail, and I hope that by the time we get to the end of our discussion, you will understand why I have put so much detail into this webinar and the materials that you will receive. Understand that you will receive all of the materials that are in this webinar, so there's no need to make any notes or worry about that. And several of the documents that are in this webinar, I won't be actually discussing in detail with you because they have been included for the very purpose of your sharing them with your learners and hopefully finding useful in your teaching. So sit back, relax, let's see what analytical geometry is all about. We're actually wanting to focus on problem solving in FET analytical geometry. And I think you might criticize me afterwards and say, but where was the problem solving? Because all we heard was simplicity. And for me, simplicity is the route to successful problem solving. So it is deliberate. So that's where you are, starting off with grade 12s right now, next week grade 11s, and then towards the end of term 2, analytical geometry. And where does analytical geometry sit in the examination structure for all 3 grades? These documents are just really useful to have together, and I've gathered in this webinar and in these materials every document that you could possibly find that could help you and find your way, that you don't have to go looking in all sorts of different places. And now what about the learner performance in analytical geometry? Well, I looked at the average performance between 2014 and 18 and found analytical geometry not too bad, 54%. Or I must say, being what it is, I do think that learners could do better, and they did. In 2019, a bit better. And what happened in 2019 was that Trig took a big dive. We are very, very thrilled to see that it is back up in a slightly more respectable spot. But what happened to analytical geometry? It is the only one whose marks went down, whose performance went down. And why would that be? And we're going to take a good look to see what happened. What happened that didn't work so well in the past? So the average performance for questions 3 and 4 were 57 and 47. Doesn't look too bad. And that is when we look at the results per question. But let's have a look at the results per sub-question. And we suddenly see here, I'll make this a little larger, that we can see that for the first part of the question, a 94% was achieved, and then it had a steady decline, 79, 69, 60, 46, right down to 27%. The results for question 4 were a little bit more jumbled, but has the distinction of the last one achieving the lowest mark for any subsection on the entire paper. You might remember those circles that were touching each other. Now, I've included in here the diagnostic report for this exam, which analyzes what learners got wrong, what they didn't understand, and where we can make things better. So the common errors and misconceptions, as well as the suggestions for improvement made by the department. I think this document is incredibly important to make a habit of following up and studying. There isn't time in this webinar for us to go into much detail. As I say, the common errors and misconceptions are given, and particular certain things that I've wanted to accentuate, and then the suggestions for improvement. The reasons I might just pop into 1 or 2 little things is to justify some of the material that you will find that I will be sharing with you. Things like, as I said, incorrect substitution into the gradient formula. Assumptions. Candidates make assumptions all the while. And particularly when they're asked to prove something, they actually assume that fact and don't read those words, prove that. Simultaneous equations. Poor algebraic manipulation was absolutely dominant in these results. Unable to use formula, tan theta equals m. There's some trigonometry, and they were unable to do that. Area of a triangle, and of course, loads on quadrilaterals always visit analytical geometry and trigonometry, as we saw recently. Writing down the values on the diagram is a very, very important aspect of success, of developing success in coordinate geometry, to analyze the diagram, and then as you proceed to write down all the values. So I won't go on any more details, apart from reminding you of this different, of the huge connection that Euclidean geometry, analytical geometry, algebra and graphs all have with analytical. So the actual exam. I have put questions 3 here, very nice to discuss with your learners, and some very interesting aspects. It is so amazing that not one single formula was required in this entire exam. So anyone who felt that you know their formulae, equipped them well enough for analytical geometry, were sadly disappointed. One could have used a formula for the first one, but we'll have a look at the attempts on each one of these sections in detail. As you can see, the results achieved had the steady decline. And what I'm going to do is I'm going to take this drawing and I'm going to focus on what the question was and what part of the drawing needed to be focused on to have learners really see how to use a diagram and to analyze what it is that they need to answer questions. So very simply, the first question was, what was the gradient of WP? And we understand that the results were high, and most people would have used the formula. Even using that formula, you know that the order of X and Y often get confused even. But what I'd like here for learners to have been able to write this down so quickly is that we've got 8 units up, 2 units across, 4 units across, I beg your pardon, and 8 divided by 4 is 2. And because the line is in that direction, it is that the gradient is equal to -2. No formula required whatsoever. What do we need to do to show that 2 lines are perpendicular to each other? We need to show that the product of the gradients is -1. And we can get the gradient from the equation of the first of line ST, and we worked out the gradient of WP in the first part. So we just need to show that -2 times a half is -1, and that is the elegant way of proving that lines are perpendicular to each other. It is, of course, acceptable to say that the gradient of the one is the negative reciprocal of the gradient of the other. What about the coordinates of S? So often, when the coordinates are required in analytical geometry, it's about points of intersection. And somehow the idea of points of intersection just doesn't come into the toolkit unless invited and deliberately thought about. And so here we very simply have 2 equations, the equation of each of those lines. But where learners went wrong was that they did the weirdest algebraic manipulation because these 2 were given in different forms, standard form, general form, and solving these were a problem. The length of WR. To find the length of WR, many learners would have immediately reached for the distance formula and tried to apply that. It wasn't needed at all. We have the coordinates of W, but the coordinates of R we don't have. We have the equation of this line. But because this line over here is parallel to the y-axis, and therefore, and the coordinate of the x-coordinate of W is -4, the x-coordinate of R is also -4. And it is these horizontal and vertical lines that learners are not prepared for when they walk into analytical geometry, and which can make life so easy for them. So simply the x-coordinate of R is -4, and -4 is substituted for x over here, y is obtained, and then the length of WR, well, a vertical length is simply the difference of the y-coordinates. So 4 subtract the y-coordinate value that we would have found at R. And now finding theta, angle of inclination. Here we're bringing in the trigonometry, of course, where there is a weakness. These questions are not answered well and need to be practiced. And of course, they require a little bit of application of regular Euclidean geometry, as in exterior angle of triangles, corresponding vertically opposite, and so on. A lot of knowledge you can hear coming in from other sections that are really needed. There's a lovely little method here by my daughter and partner, Gretel Lamper, of many years, that one can put in a little system of axes right here at S. And as I will show that in the next slide, which then requires us simply to find theta by adding 2 angles easily acquired from the tan of the angles, giving us the angles of inclination, and from that simply being able to do that. So that's quite a nice little technique, a very nice original and novel one, and makes that example very easy for learners and very approachable, accessible. The area of a parallelogram, it's amazing how few learners actually know the formulae for the area of quadrilaterals. And so the area of a parallelogram being base times height. And I must say, this examiner really had vertical and horizontal lines in his or her mind, because to find the base, it simply was the length of WR, which we found from question 3.4, and then the height was this horizontal line. And from -4 to -20 is very simply 16 units. So that made it very easy to find the area of this parallelogram, the base and the height, very easily obtained. And these coordinates, of course, were found in question 3.3 and were entered on the diagram if the correct procedure was followed. Question 4. Over here, the jumble of results, and then this disastrous 4.5. And look at this drawing. I said that drawings never looked like anyone had ever seen before. What I have attempted to do in a lot of the work that we present is when there is a very text-heavy question, I like to separate it in bullet points. It does make it more accessible to learners, especially learners who are learning and studying maths where English is their second language. It is really important to separate the facts and deal with each one separately and really become absorbed in what the drawing is containing. Again, over here, equation of the circle. We just take out the circle, center the origin, and all we need to find the equation of such a circle is the radius. Whereas in the next question, when we have to find the equation of a circle where the center is not the origin, we need the center, the coordinates of the center, as well as the radius. And Euclidean geometry teaches us that a tangent is perpendicular to the radius, but there must be an awareness of this visiting of other topics in the middle of any one particular topic. So knowing that this is perpendicular, again, we have, believe it or not, another vertical line. And so if the coordinates of n are -11, then we know that the radius of this circle stretches from -3 through to -11, because the x coordinate over here is -11. So the radius is 8 units, which makes it very easy. We know the radius, we know the center, to then write down the equation of the circle. I see I've omitted to put the brackets around the point. Forgive me for that. The equation of line NM. To find the equation, we have a point, and so we analyze what do we need when we need to find an equation. We need either 1 point and the gradient, or 2 points, or the gradient and the y-intercept. And in this case over here, we again have a tangent to look at as giving us what we need, because it is perpendicular to that line. And we know the relationship between the gradient of the gradients of perpendicular lines. So if we have the gradient of this line, the diameter, then we can easily find the gradient of that line and therefore the equation of NM. The length of SN. Again, when asked for the length SN, we do think about formulae, and I think this time maybe we did need formulae because, you know, needing those coordinates. But now, what do we have? We need the coordinates of both points. The point S was found by reflection, so we have even translations being used here. The reflection of M in the origin gives us those coordinates. And over here, we found that the equation of NM with x equal to -11 substituted will provide the y coordinate that we need, therefore enabling us to get the length of SN. Now, the values of K. And I must say, I do love to picture where you all are right now and wish that we could actually be together and see one another. And so if you want to put up your hand to say that you actually didn't think of both options when you were working out this question in the exam at the end of last year, nobody will see your hand going up. My hand would certainly be up and you could see that. I didn't realize it at first. And so it's become a very interesting conversation. And in fact, so interesting because although I'm thinking about this points of intersection and particularly between circles as being a relatively an aspect that has received more recent attention, I actually discovered that it existed in the exemplar paper after all. I've said to you those exemplar papers are magnificent, but yes, had we studied those, we would have been thoroughly prepared for this question. The memos have just been included for use for your learners. For convenience, and of course there you see the solution to that infamous questions, shall I say, but exciting. So the content of analytical geometry, according to the curriculum and according to most of our minds, we think formulae, yeah, and then grade 11, the angle of inclination, and an in-depth deal with dealing with straight line graphs, and then finally grade 12 circles. And I do think that we underestimate what analytical geometry is about when we just look at that. So let's expand a little bit on this content and list some pre-grade 12 issues that come up. Graph concepts, as we've already seen in the discussion that we've just had, are absolutely crucial, and a very good and deep understanding of straight line graphs, which will follow soon. Quadrilaterals are also extremely important. And then circles. it's not just circles, it's equations of circles, and as we've seen, with the center of the origin or not. And then we will also have a look at general and standard forms of the equation and the conversions required. The tangent to a circle, we've also come across in our example, and then the points of intersection as a major role player in this topic, between both a circle and a line, as well as between two circles. So I think it's really important to share, and I won't go into all of these slides in detail, but to share the different sections that analytical geometry require, so that we're aware of all of these separate things. And most of these concepts are brought in to the geometry, the analytical geometry toolkit, which I mentioned earlier. Equations of straight line graphs, we will be looking at 3 cases, because I think that learners are inclined to just know the straight line graph has the equation y equals mx plus c, and beyond that, there is no further knowledge on the straight line graph equations. And I feel very strongly that this is a wonderful opportunity for learners to really expand their comfort in straight line graphs, but actually in graphs in general. So I will really focus on this area in a little while. Quadrilaterals, I nearly didn't bring it in too much here. We really did focus quite heavily on that in the geometry, but look at all the incredibly important aspects that learners actually need to know about quadrilaterals. So we expect a lot from them. And your grade 12s who have just walked in, I mean, they missed so much work last year. And apart from that, the memories of learners on even work that they would have done the previous year aren't always so great. So conscious of the fact that they have been deprived of many hours of tuition and work in last year's COVID, it has made us actually focus on the pre-knowledge that learners require in all topics. And so it's actually a great benefit, because I think the need was there all along. It's just now had a spotlight thrown on this need. And then those topics that I mentioned in circles. And over here, we say to ourselves, how on earth are we going to catch up all that previous work? There's just no time. You have 2 weeks in which to do analytical geometry in each of the grades. And I've previously recommended the fantastic use of these exemplar papers. But I think it's a really good idea to give your matrics, say for instance, just this one grade 10 question, you know, give them a couple of days and say, just go through that and just master those few concepts and issues. Then give them the grade 11 questions. And in no time, you'll find them coming a little bit more up to speed and being a little bit more in readiness for when we get to the grade 12 work, which maybe we think is all about circles, but just look what is all around here. Trapezium, coordinates of a midpoint, coordinates of, or the gradient, the angle of inclination, points of intersection, all work that actually appeared earlier in the curriculum for analytical geometry. And of course, my big thing that I will get boring about saying is to request that your learners use the diagram to do all their work. The memos are there for your convenience for grade 10, 11 and 12, and you could give them as tutorials for your learners to actually catch up on their own. Often when learners are not able to come to school regularly, this is a wonderful piece of work which they can get on with and guide themselves and actually understand what it means to be an independent thinker and learner, which is so critical if anyone is to have success in matric. We as teachers, even if we saw them for 24 hours a day, could never teach them everything that they need to know. They need to take responsibility for their own learning and use our experience and our guidance as their light. So the much mentioned toolkit. We consider that there are 4 drawers in this toolkit: formulae, graph concepts, straight line graphs, and circles. And it's so important for learners to see that all this knowledge that they actually need to have at hand to be confident at answering analytical geometry questions, the summary of all of this knowledge can fit on to 2 pages. And that is always very encouraging. But they really need to know all of these things in great detail. And over here, only the formulae have been given, and the approach to these formulae will be coming up in a minute. How well do learners know the gradient of a line? Do they immediately know positive, negative, zero, undefined? Do they know the relationship between the gradients of perpendicular lines? And just by the way, do they know why perpendicular lines have that relationship? I can't go into that right now, but it just brings me to a very important aspect of mathematics in general, that I don't like learners to use any fact that they for themselves have not proved and do not for themselves understand why they are so. And then, of course, parallel lines have equal gradients, and the whole concept of collinear points. Very simple, but the learners need to really focus on them and be confident about that. The inclination of a line, graph concepts, axis-intercepts, equations of graphs, types of graphs, and these two really important facts, absolutely crucial. Points on graphs. It might sound very, very simple, but if a point lies on a graph, the equation is true for its coordinates, so substitute. And conversely, if a point satisfies the equation, i.e. makes the equation true, then it does lie on the graph. Very, very simple, but fundamental to so much understanding. When we, for instance, look at the equation of a circle, so often when learners have to find the equation of a circle and they say the radius is given to them as 5, then they forget to give 5 squared in the equation. And maybe it's because they haven't realized that what this equation is actually the statement of the theorem of Pythagoras. That true for any point on the circle is that the sum of the squares of their x and y is equal to the square of the radius. And that is the theorem of Pythagoras. And even when the circle does not have its center at the origin, we're again dealing with the theorem of Pythagoras. And that then becomes the general form of the equation of a circle. I earlier mentioned points of intersection as being a vital area of analytical geometry as well. And then straight line graphs. The standard form y equals mx plus c, not being the only one. And then it too, having a standard form and a general form, just like the circles. And where in the circles, the converting is terribly important and mentioned here and to be studied. Tangent to a circle we've mentioned, vitally important, and especially as we had earlier in the example with regard to the gradient. So we know because of the perpendicular lines, the relationship between the gradients. And then just a nice little summary here of points of intersection where they exist between a line and a circle. They are either 2 or 1 or none. And that number is also the number of solutions that you would have in solving the equations of the two graphs. In this case, 2 solutions, 1 solution, and here no solutions. So if ever we have to prove that a line touches, and often the word tangent isn't even used, just the word touch means we have to prove the line is a tangent. All we have to prove is that there is only 1 solution when we solve the 2 equations of the graphs. Final advice, use your common sense and always draw a picture. So that is a lovely summary, a toolkit, to be sure that all your learners have lying on their desks in hard copy to refer to in an instant, if ever they struggle with anything in analytical geometry. So the formulae. It's so important that learners learn from regular numbers, which they can envisage and understand. And this is one of the most important diagrams that you could possibly give your learners before they learn any formulae. And in fact, they shouldn't learn the formulae. They should develop them for themselves and summarize them for themselves. And then they will just always know them. They will not ever need to even reach for a formula sheet. So I've got all these question marks here, which are the fundamentals to the understanding of formulae. And first of all, to know that if the coordinates of A are 2 and 3, that answers those question marks, and 8 and 7. And then really critical here is the vertical length, which we referred to a moment ago, as the difference between 7 and 3, the y coordinates of B and A. 7 minus 3 will give us 4 units here. And then the x coordinate over here is 8, the x coordinate there is 2, and this length is 8 minus 2, which is 6 units. Terribly, terribly simple, but so crucial that learners are completely comfortable with that. And then to fill in those values for themselves. And then it becomes really, really easy to apply the theorem of Pythagoras in order to determine the length of AB, and continuing to use numbers and arriving at their answer, and focusing on the importance of the horizontal and vertical lengths, which we saw being applied in the raw in so many cases in the exam, which learners did not do well in. And we wonder how much of it was actually rooted in a lack of understanding of these. The distance formula can now be very easily understood. So if the coordinates of A and B are x1, y1, x2, y2, then we can understand the vertical length is y2 minus y1, and the horizontal length is x2 minus x1, and we can then completely easily conclude the formula for the distance. And the gradient similarly, also again become acquainted and do it with just the numbers. And understand there that the horizontal is the difference between the x-coordinates and the vertical length, the difference between the y-coordinates, so that this becomes something that learners are really confident about. And then the gradient formula can easily be derived by them and remembered by them as the difference of the y's over the difference of the x's in the same order. The midpoint of a line segment. Here are the question marks. Should be put to learners. What do you think the coordinates of that point would be, and how do you think we could get it? To arrive at the fact that it is midway between 2 and 8, and the number midway between 2 and 8 is the average of 2 and 8. 2 plus 8, 10, divide by 2, 5. And the average between 3 and 7, 3 plus 7 is 10, divide by 2 is 5. And yes, actually, we could have guessed that that was 5 by inspection. The number halfway between 3 and 7 is 5. So important to have multiple approaches to the way we can see things and what we can read of our diagram with our common sense way before we reach for any formulae. So over here, we understand that the x-coordinates are the averages, and I have accentuated there for the plus signs because a very, very classic error with learners in the exam is to put minus signs over here. And if they've understood that the x and y coordinates of the midpoint of a line segment are the averages of the x's and the y's, then they will remember the plus signs very easily. Gradient of a line, we've discussed that. Just very important for learners to just have it all at hand, and then to see that the gradient which we used just now, the formula for that, which was y2 minus y1 over x2 minus x1, we recognize that when we look at an angle here as being the opposite over the adjacent of this angle. And so the tan of that angle is equal to the gradient of the line. And we use that fact to establish the angle inclination of a line by getting the second function of the inverse function of the tan value. If a line makes an acute angle with the x-axis, then we know the gradient has to be positive. And if the angle is obtuse, then the gradient will be negative. And to have an awareness of that. I have here a lovely little investigation of the common sense approach, which I would love you to share with your learners. And that is to have them establish in what I will call case 1 lines, case 2 lines, and case 3 lines. Because I find there's only an awareness of case 3, but let's see what we're talking about. Vertical and horizontal lines are what I refer to as case 1, and we've seen plenty of them in this webinar so far. And to ask your learners to, by inspection, write down the length, the gradient, and the midpoint, and see how many of them want to rush to their formulae in order to do that, and to find that it's absolutely not necessary. The length of this line is so very easily to see, easily seen as 4 units. And the length of this line as 6 minus 2, also 4 units. The gradient of this line, undefined. The gradient of this line, try a formula. You will struggle to find the answers undefined and even 0 from using the formula. And then the midpoint. The midpoint will have x-coordinate 2 here, and then of course 5 as the y-coordinate. The y-coordinate of the midpoint will be 3, like those two, P and Q, but the x-coordinate will be halfway between 2 and 6. I've just included the answers just to share with your learners, and then case 2. Case 2 are lines that go either from or through the origin. And what we know about those in our regular standard form y equals mx plus c is that c will be 0 for all 4 of those cases. So let's give this instance, or this case, its own general form. It is simply y equals mx because c is 0, which means that all one needs to actually know is the gradient. And since we had the gradients, and since we were asked the gradient in the part B over here, we could immediately just write down the equations of those lines without thinking any further or getting too complicated. So now what about case 3? Case 3 is what is generally thought of as our y equals mx plus c. And over here too, the establishing of vertical and horizontal lengths in order to, again, by numbers, find the distance and again have it confirmed in our formula. And so to the gradient. And in this case, continuing on to calculate the angle of inclination from the gradient 1/3 that we obtained over here as being the inverse function of a third of the inverse function of tan. And to so really understand that. The midpoint, seeing there the averages, and again establishing that learners can actually derive these formulae for themselves and have those pluses in place. The graph concepts, really important for learners to revise and study, especially the equations of the axes. The fact that every single point on the y-axis, true for it, is that x equals 0. Qualifies x equal to 0 as being the equation of the y-axis. Similarly, y equals 0 is true of every point on the x-axis, qualifying it as being the equation of the x-axis. And then, of course, knowing that various types of graphs have various standard forms that we've come across. And the points of the graphs and the points of intersection I've discussed before. Let's have a look at the standard forms. There are 2 main standard forms for the equation of a straight line, actually, not just y equals mx plus c, but also y minus y1 equal to m, x minus x1. And we've seen how y equal to mx plus c could have c equal to 0, in which case we get y equals mx, which is case 2, or we could have m equals 0, a case 1 line, y equals to c. And that y equal to c is a horizontal line, which we can sort of see we can derive from y equals mx plus c. But vertical lines cannot be derived from that. They have their very own. The equation x equals k doesn't fit any standard form. It is its own standard form. It is the standard form for all vertical lines. There is a bit of an aversion to this, and for that reason I've put in a slide which hopefully will make it more comfortable and will tie in with the conversation that we've just had, and that is that the gradient of a line is the difference in the y over the difference in the x. So y minus 3 over x minus 2 equals m, and a simple multiplication by the denominator gives us that. And if instead of a fixed point, we 2, 3 with values, we take x1, y1, we can understand why y minus y1 over x minus x1 gives us the gradient and where this comes from. I really do encourage learners to use this. It is so much quicker in calculations than using y equals mx plus c, and very, very useful, especially for matrics, very necessary. Finding the equation of a line, case 3. So I feel this is an area where people are generally much more comfortable. And so all I'm going to do here is mention 3 examples in which there are a few cases of each, that in order to find the equation of a line, we analyze. What do we need? We need m and c, or as earlier, m and a point, or we need 2 points. And just to make sure that your learners, if they have a little bit of a weak history of knowledge of the equations of straight lines, that they get some practice, and then to follow would be all the each question with its solutions. And I have put in some nice surprise ones here. A line passing through those 2 points. Of course, they would have gone immediately and found the gradient using it, and they would have got into a bit of trouble because they would have found 0 in the denominator, because if they didn't notice and didn't first draw and sketch where those points were, they wouldn't have realized that this is a classic x equals k, and that it doesn't fit any traditional equation, y equals mx plus c. So a couple of little surprise examples in between, just to remind them that the sketch is so important to do before being led blindly by formulae and rote methods. So I'll move on to, after that, there's another one of those, just to test that they're on form. And then, just like the circle has a general and a standard form, so does the equation of a line. So the general form of the equation of a line is this. And the most important thing that I want to say about that is that I would say a huge majority of learners, when asked a question like this, would immediately proceed to want to write it in the form y equals mx plus c, because that is their comfort zone, and to say that it is absolutely not necessary. Graph concepts will show that if we're looking for a y-intercept, all we need to do, no matter what graph, no matter what equation, all we do is to substitute x equal to 0. Then we get 3y plus 6 equals 0. 3y equals minus 6, y equals minus 2 is the y-intercept. We substitute y equal to 0, we get 2x plus 6 equals 0. 2x equals minus 6, and x equals minus 3 will be then the x-intercept. And we can then draw the graph, and we will be able to, from the graph, write down the gradient of the line. Of course, interesting is to then rewrite this in the standard form to check that our answer to B is correct. And now what about some other non-standard forms of the equation? There's the general, but there are these. And the same applies to these. We need to just put x equal to 0 to find that the y-intercept of this line is 5. And we need to just put y equal to 0 to find the x-intercept of this line is 3. And there we go, we can draw the graph. So I really would like to unlock this sort of closed approach that somehow we grew up with a lot in algebra, I have to say, and what analytical geometry can do for our thinking and expanding it. And there's the dual intercept method. I could not leave out quadrilaterals, our brief little trip through that, and all the things that we need to consider to encourage learners to think about all these aspects before I give you this frightening summary, which is really important, but it does contain all the facts that learners need to know on quadrilaterals. So if they missed out on any studying or learning about quadrilaterals last year, then this would be ideal to share with them. So somehow I think that circles we're a little bit more acquainted with. Fortunately, I've discussed this and that equation as well, the general, and then the conversion from standard to general or form, which we do for a straight line as well as for a circle. Converting from standard to general form is very easy. We just multiply out. But we find it tricky when we have to reverse this. Unfortunately, I can't go into this much now, but I have included a few valuable slides on the completion of squares, because I hate learners to just by rote learn. I just have to halve the coefficient of x and square it. Let's go back to the beginning and see what happened. What happened when we had a square? We arrived at that trinomial. How do we get back from that trinomial to the beginning? And we can see that we halve the 6, we get 3, we square it and we get 9. Give them a couple of examples where they multiply out and then reverse, multiply out and reverse, to be comfortable with doing the following exercise, where now they can use their little formula once they've developed an understanding for it. We've spoken about the tangent and about this concept, of course, earlier, but I wanted to link this concept to our algebra, where we also sometimes look at a line cutting a parabola, and that the same concept applies. It is so important to integrate different topics in maths and see that the same concept is behind it. That when we're looking at a tangent to a circle being perpendicular to the radius, we can also see that the derivative of this line, it being a tangent, is very important, and we know that the tangent will be, or it will be a case of a tangent when we solve the equation and find one solution. So all those different concepts coming together. And this really interesting fact, I'm so pleased I'm running out of time, because this is quite a complex little situation, which I would like you to keep as simple as possible and not to scare kids or yourselves with it. But I have decided I have to include these two slides for further consideration. I have run out of time. I so badly would like my colleagues to have a chance to answer your questions. And so just to say, I've given some lovely questions here which demonstrate that, for example, from a general form of the equation of a circle, you cannot determine the radius or the center, and you need to convert. So what is behind all the thinking in our examples? So I've given a number of really good examples, you know, or thorough examples that you can share to apply all the concepts that I've offered in this webinar, the materials of which you will all be receiving. I love those tangents and the relationship with the circle. Of course, I love my horizontal lines and how they link in and just visit so much of analytical geometry. So all those examples, and of course the final advice, use common sense and always draw a picture. Our grade 12 maths offers plenty of practice and exercise. Please read about it. I have no time to mention anything about that now. And please do look at the challenging questions on analytical in the 3rd section of our book. Our free ebooks, I don't know if you're aware of it, but all our study guides are available freely as ebooks to all teachers in the country. And that is the link for that, and an interesting video link as well. Thank you very much. Just useful documents on the curriculum, which obviously is just there for your convenience. Thank you very much for your patience, and I've enjoyed it. I hope you've had fun. And over to George and Jenny and Susan.
Fantastic. Thank you so much. And we're looking forward now to, we'll just wait for the feedback to continue. Mom, can you unmute? I mean mute, sorry, thank you. Great. Okay, so we're now heading into some reflections on analytical geometry. I put a link in the Q&A. Please, can you offer your contribution of what stood out for you today that was very valuable in our quest to make this the best form of teacher professional development in South Africa. And also, while we're doing that, we'll take your Q&As. So please pop those in the section. While you're doing so, I'll offer the floor to Jenny first and Susan second to offer any reflections that they might have. Jenny, as Bishop's head of maths last year and joining us on the team, and then Susan, also head of advanced program mathematics at Rondebosch last year, joining us at the team at the Answers series. We're really wanting to give you the best form of maths teaching and teachers to expand your knowledge. And so Jenny, any further comments that you would like to offer at this point?
I think for me, having just worked with Susan on preparing a micro course on analytical geometry, a growing awareness of the challenging problem-solving questions that the section has. So I've, like many teachers, often thought analytical geometry can be somewhat dull, but actually, if you really look at the questions and if you look at where the examiners are going, it's rather exciting to see the different things that one can ask. So you are setting the exams in your own classrooms, and the examiners, I think analytical geometry is starting to come alive now that we've got past the basics and everybody understands it. So if I can emphasize one thing, it is look at your sketch very carefully and always think about, is there actually only one answer here, or are there more answers? Because when I get tripped up, it's usually because I found the quick, obvious answer and didn't look deep enough at the question and realize that there's another one hiding or lurking somewhere. Yeah, that's it from me, George.
Excellent, Jenny. Thank you very much. Susan, have you got any reflections?
Yeah, I promise I didn't check with Jenny at all in this, but my big things are, I want to encourage you all to do the micro course. With the problem-solving questions in particular, take up the challenge and try them before we show you the solution. And it might not be the only solution. You could very well have done them in a far more efficient way than we did, because often with problem-solving questions, there are multiple ways of doing things. And I think it's so important to expose your learners to level 3 and 4 questions. Let them play with them, let them try them. Don't give them a solution immediately. But if they are starting to get stuck, then give them a hint and then say to them, now, keep trying it. Because they get such a sense of achievement when they can solve a difficult problem. So I hope you enjoy the micro course that we've put together, and good luck with teaching of analytical geometry this year. Thanks.
Excellent, Susan. Thank you very much for that contribution. All right, so we're going to actually look at a couple of questions. When will the materials be available? Can you please post a link for free ebooks here? How important is it to teach the circle intersections to really struggling learners who may lack basic concepts? So Jenny, would you like to take that last one? How important is it to teach the circle intersections to really struggling learners who may lack basic concepts?
I think if you go into the extreme of the fact that there are multiple solutions, it might be overwhelming. But if you do it visually, so I'm a very visual learner myself, and if you give them two circles and you simply show them that when two circles touch externally, the only way that's possible is if the sum of the radii is exactly the same as the distance between the center points. So that question is answered simply using the distance formula. And even if you work internally, if you do it with a diagram, don't teach them a formula, show them on a diagram that when two circles touch internally, you literally just have to subtract the radii and make that equal to the difference between the center points, the distance in the difference. Well, that didn't come out right. If the distance between the center points is equal to the difference between the radii, then the circles touch internally. So if you learn it like a parrot, it's not going to work. But both methods simply require the distance formula, which is actually regarded as basic knowledge. So I think it is important to expose your learners, because with your luck, you won't do that and then they'll get a 7-mark question and you'll feel really awful. So don't underestimate the ability of kids to absorb things that we think is difficult. For them, if it's visual, they actually remember it.
Excellent, thank you very much. I'll be asking my colleagues in the background to post the ebook links here. When the materials will be available, the materials will be downloadable from within the micro course. Okay, so there's a link in the Q&A. Take a look. You can access the micro course immediately from now, in fact. But there's a couple of things that I'd like to take as we exit today's session and end promptly at 5. So just first off, thank you so much for joining us and squeezing the session into your calendar. I have now loaded those links, as I've mentioned. For those of you who don't experience it already, your life is made a ton easier when each learner in your class has the TAS study guide. And so teachers say that method marks is where learners really improve. And when they use TAS study guides, the learner repeatedly is shown the model answer methodology for each practice question. So this is a shameless punt of our study guides because we know it helps learners so much and teachers even more so. So to any of you who have yet to order your study guides, we're actually providing a promotion for the month of May. In addition to the normal volume-based discounts that go up to 20% off, we'll provide a complimentary EULA ruler for each book purchased. So simply send us an email with May Maths deal or some version of that anywhere in the title, and we'll support you to get the deal. Or click the link in the chat box, which I'll post there now about that'll make it easy, and we can send you a quotation to get the ball rolling for ordering for your class. So I'll pop that link in now, which is that's the one that'll set you up for orders at the answerseries.coza. Without any further ado, a huge thank you to all of you for joining. A huge thank you to the Answer Series team, those who spoke today and those in the background to put it all together. Great appreciation for everyone. And for now, good evening and goodbye.